Welcome everyone. In this video I'm going to show you a cool instrument which is inside this enclosure, and it can measure weight much more precisely than a traditional load cell. So let's open this thing and let me show you what is inside. So this is the inside of the instrument. It has many interesting parts, and I'm going to guide you through all the parts. So you will see everything around this construction, how it works, why it works as it works, and what we can use it for. And before going into more details, I just want to tell you more about this device. So this is originally from a thermogravimetric instrument, which was used for measuring, for example, oxidation properties of steels. And I managed to save this part of the instrument, which was destined to be thrown out. And I think this is one of the most interesting part of that instrument, so I just took it home. And due to the principles how this thing works, it can measure weight changes or weight extremely precisely. So this can measure even in the micrograms level, but of course you need to calibrate it and so on, but it has a very delicate mechanism and sensor. And why this wall thing was in a metal enclosure is because actually this wall mechanism is or can be evacuated. So actually there was a rubber sealing here, which I just removed, but yeah, so everything is under vacuum or some sort of atmosphere. And then under this wall enclosure or metal dome, the instrument actually is continued downwards. And then what happens is that on this side of the arm, there's a big chain hanging, and at the end of the chain, which can be like 40-50 centimeters downwards, there's a hole there, and the chain hangs through that hole. So at the other side, there's a small basket, which is made of some kind of inert metal or ceramic, and you can put your specimen there, and then that whole basket and stuff is hanging in a furnace. So then you can heat up the specimen by turning on the furnace, and then based on what kind of specimen you have, for example, if it's some kind of metal, it suffers from oxidation if the furnace contains some kind of atmosphere, and then due to the oxidation it will gain weight, but obviously just a little weight because yeah, the oxygen atoms are not so heavy. But if you let it oxidize for long enough, then actually it will change its weight in a detectable amount, and then this guy here will be able to detect it. Or if you have some kind of polymer or some volatile compound in your device, then if it's volatile, then it will lose weight, and in the same manner you can measure the weight loss with this device, and then yeah, evaluate your test results. But in this video I will just show you how this thing works. I don't have the rest of the equipment, so I cannot do any measurements and I cannot calibrate it, but I think the mechanism itself is so genius that it is worth to dedicate a video to it. So let's take a little closer look at this mechanism, and I will show you how it works and what are the principles. So I already told you that here we have the balance arm. So this side is the, let's say, measuring side, and then here the back side is the balancing side. Because when you initially set this system up, then you have the chain hanging down here with the sample holder, and then on this side there is typically a small basket where you can put small metal balls in. And then what you can or have to do is that you set up the wall system, and then you make it balanced, so you cancel out the weight of the chain and the sample holder by placing weight in the basket placed in this side. And then that's your like tiered let's say, weightless or massless arm, balance arm. And then you can see that there is a stick here. I will show it from a closer perspective, or maybe from a different perspective, but that stick is actually attached to the center of this arm. So then whenever the arm is off balance, so it's moving some way, then this stick moves together with it. And then that stick comes up here to these 4 solenoids, and from this center metal piece, there are 4 metal rods going into the 4 holes of these solenoids in total. So then you can suspect that something is happening with these coils or solenoids here. But then when we go further up here, at the very top of the picture, I will also show this from a closer perspective, then this stick continues upwards, and then there is a metal plate there with a slit in its center. So then these coils and that metal plate with some light source and light detectors make this wall balance mechanism work. So let's see how this works. So first let's look at the balance arm again, because there are more details that I want to explain. So here on this side there is a metal plate, and similarly to that there is a metal plate here as well. And they are pushed inwards. You can see that they are slightly bent by some screws. You can probably see that there is a screw up there, and on the left side it is a bit more shiny. You can see another screw there. So this is just to fix the balance arm when you try to, let's say, transport this thing. So then you don't destroy that tiny metal line there, which is a torsion line. So actually, when I unscrew these 2 bolts, and I show you in a few moments, then this plate and the other plate will bend backwards, so towards the 2 sides of the picture. And then that will put some tension on that line. But that is still not enough to release the balance arm, because here you see this knob here, and that is pushing down this arm, which is at the end pushing down this foot, and actually it's feet, because there are 2. There is one more right here on the other side. So what happens there is that they push down the wall arm, so the arm can rest on this rubber support and this rubber support here. So then it's totally safe to move it around. So to demonstrate how to unlock this, I will start with this screw. You can see that there will be a gap opening here. And this should be enough. And then I will just unscrew this a little bit. And you can see that the line is getting more and more stiff. Now it moves the balance arm, but I have to release it from the other side as well. So that's done, and I need a bit more release here. So now the arm is released, and it is purely hanging on that torsion line there in the center. And you might have noticed that I knocked off some weights from the hook here. So I put them back. So this is just a simple washer, and this is just solder material, so just some tin. And there is an identical washer on the other side, but since I have this very tiny extra weight, then the arm is off balanced towards this side. Now I bounce the arm a little bit, and you can see that it moves. So it's still moving freely. So now let's go up to the coils and see how they work. Okay, so now we are looking at the coils. So as I said, this is attached to the balance arm, and you can see how they move together. So what happens here is actually we have a circuit here with these 4 coils. And how it looks like is the following. First, the circuit comes into this coil, and then it goes to the other coil behind it. And then it continues to this side. And then it goes to this coil first, so the coil in the back. And then the circuit comes into the coil in the front, and then it goes to the other side of the circuit. And how it's set up is that this wire here will be the positive side. So if we, let's say that it flows in here, and then it goes to the next coil, comes back, and then goes into the coil in the back, and then goes into the other coil, and then it comes out as the, let's say, negative pole. So then I measured the resistance of these 4 coils. They are connected in series. You might have noticed that as I explained it. The total resistance of this is 54.4 ohms. So it's quite low resistance, and therefore it requires a very low voltage to make any kind of, let's say, noticeable current flowing through the coils. And also the wires in the coils are quite thin, so you don't want to rush too much current through it. But yeah, you might know it from the school that if you have a coil and you run current through it, it will generate a magnetic field. And that's one of the elegant things here, is that obviously these rods react to the magnetic field. So therefore, what we actually have here is basically a servo motor. You would expect, of course, a motor to make a spinning motion, so don't take it as a very serious expression, but it's a servo thingy. So you give some current through these coils, or run some current through these coils, and then based on how much current you run and what is the polarity of the current, this will move to some way. So then when, for example, in our scenario, we will have a weight gain, then the left side wants to go down, which will move the arm to this position where it is right now. And then that's the genius part of the balance, that how do we know how much weight is hanging on that side where we have the washer right here? Well, in order to make this balanced, it has to be in the center, right? Somewhere there. So to bring it to the center, you have to run a certain amount of current through these coils. So then you can guess that actually the current is proportional to the weight which is hanging there. And then if you run that current through a known resistor, then you can obviously measure the voltage, and then you can run that voltage to your AD converter and then measure it. And then by knowing that voltage or current, it doesn't matter, because in fact you just have a multiplication factor between them, which is actually just the resistor that you have in series with the coil or coils. Then yeah, you can basically relate the voltage to the weight. So that's called calibration as well. So you can put different weights on this arm, and then you can read your voltage. So then you will have a certain weight versus certain voltage, and then you can do this with many weights, and then you can have a hopefully linear correlation between the weight placed on this arm and the voltage needed to balance out this mechanism. Unfortunately, I don't have those tiny weights at home, or not yet. If you have, please send me and I can do the calibration and everything. But yeah, I cannot do it, so I will just present you the principles now, and once I get some weights, I will do the calibration, and then we can measure funny stuff, for example, evaporation of water or ethanol or something more volatile, just for fun. Okay, so now we are at the point that we have the knowledge that we need to generate some magnetic field with these coils in order to move the arm to the center to make the arm balanced, and then based on that current or voltage that we have to make the arm in the center, we know the weight, right? But how does this device know that it is sitting at the center? Well, let me introduce you to this balanced photo detector. So, as I said, there is a metal plate here with a slit in the center. So if I move the arm, you can see that this goes back and forth. So here, this is a simple red LED. Of course, you will see this in action soon. So then light comes here, and then it shines at this plate with the slit on it. But then the more interesting thing is here. What we have here is there is a hole here roughly, and there is another hole here roughly. You can kind of assume by these three soldering places here where the pins are soldered. And those are photodiodes. So there are actually two photodiodes inside this block in series, and they detect the incident light. And that is what I simulated here. So actually I also just printed this block, and then there are two photodiodes in series in that block. And why do we have that? So you can see that there are like three pins here. One is the positive bias or positive input voltage, and then the next pin is the output pin, and then the third pin is the negative pin or ground. So then what happens is that the light from this LED shines through this slit, and then based on the position of the slit, the two photodiodes which are sitting in this block will be lit up differently. So they will have different incident light, different amount of light, depending on the position of this plate here. And then if you bias these photodiodes, then they will actually, let's say, generate current according to the incident light or the intensity of the incident light. So then what will happen is that since they are in series and they have different currents generated, there will be a net current appearing on the output pin, which is the center pin. So if we translate this concept to, let's say, a voltage divider, then this is the output pin of the voltage divider. But here we have more like a current divider, but it's in quote marks because it's not really dividing the current. So then we bias this series of photodiodes. Then here a current will come out, and then we can measure that. So then what will happen here is that if this is perfectly centered, then the photodiode's supposed to have equal amount of light. And then that's how we will able to know that the mechanism is balanced, like mechanically balanced. And then since we know that the system is now sitting in the balanced position, we can read what is the current that is running through the coil, or what is the voltage, which is read through our current sensing resistor. And then we can correlate that to a weight. And then again, we can put more weight on the arm or remove weight, let the thing balance itself. And then we read the current again. And then we know that, okay, the weight B has this much current, weight C has that much current, and so on and so on. So now this is basically our feedback right here. So actually this can be put together with an op-amp circuit or with a microcontroller, and then the microcontroller can read the current from here, and then based on the reading it can decide whether it should increase or decrease the current running through this coil, and then it will iterate this loop over and over until the balance is found. And then when the balance is found, then we note down the current, and then we are happy. So as I said, I cannot show you like exact weight measurement, so I cannot show you an absolute value that I'm measuring, let's say 29.7 micrograms, but I can still show you how this works. I just won't be able to show you absolute values. But let me wire up this system and I will show you how it works because it's very interesting. So here is the wall test setup. And actually everything is powered by an Arduino because we are using basically 10 to 20 milliamps total. So it's nothing. Arduino can provide that much power even through their GPIO pins, but I'm using 10 milliamps or 20 milliamps from the 5-volt rail, so it's even more safer. You can see that we have two multimeters. They have different purposes. Let's start with the Arduino. So I use this Arduino because I have a DAC here, a 12-bit DAC, which is a very good tool because it has 1.22 millivolt step size between 0 and 5 volts. So that also means that I can regulate the current very precisely. And this specific chip can go up to 25 milliamps, so it can source current, and that's what I will do. So this will be the current source for the coils, which I showed you. And then what I do is that you can see that there's a clip here that goes into the multimeter first. It will measure current. So then current goes through the multimeter and then goes to the pin of the corresponding side of the coil. And then the coil is finished. And then the current returns. And then it goes through this blue wire to the negative supply pin or ground pin. And then we have this blue line that feeds the LED that is from the 5 volt and then through a 200 ohms resistor. Then we have this red clip that is through a 2K resistor, and that is actually feeding the line towards the two series connected photodiodes. And then the output of the photodiodes is coming out on this white clip, and then it goes into a resistor, a 1K resistor, and then that 1K resistor is connected to the ground, but at the same time that goes into the ADC of the Arduino. Plus we have this clip which will also measure voltage with this other multimeter. And then here is a black clip in the background, and that is just the ground of the LED and also the photodiode circuit. So then that also goes here to the ground pin or ground rail. And what the Arduino does is that I can rotate this rotary encoder, and step by step, so basically by 1.22 millivolt step size, I can regulate the output voltage from the DAC, and that at the same time kind of regulates the output current that is then provided for the coils. So then what I'm going to do in this demonstration is that I will try to increase the current as much as I can do in order to reach a balance here in the mechanism. And if we reach balance, then that means also that the light which shines through this direction and through the plate with the slit should reach the two photodiodes basically equally, and that should cancel out their current. So then when we try to read the voltage here with the AD converter or with the multimeter, then we should read 0 or close to 0 voltage. And here I again want to re-emphasize that this wall mechanism is inside a very thick metal thing, a dome, and that dome seals it from, for example, draft, because when I'm talking and stuff, I can influence this very sensitive balance mechanism. And it also seals it from any kind of light source, any other light source which comes from this LED that is excluded from the light, which can be picked up by this series of photodiodes. So then the experiment won't be perfect in this scenario, because I cannot turn off all the light sources, cannot, let's say, seal it off. And also, as I'm moving around, breathing and stuff, I will, unintentionally affect the measurements. But I still want to demonstrate it to you, so you can see how it works. So please don't expect like totally perfect results, because the circumstances are not perfect. So I changed this perspective a little bit, so you can see everything. And what you should focus on is the display here, the display here, and the display here. And then you should try to see how this plate moves when I crank up the current. So first, let me connect this thing here. So all I'm doing is that I just connect this plug to the COM or negative side of the multimeter. Then I turn it into milliamps mode, so it's now no current is flowing. Then this goes on. This will be our voltmeter on the output of the coil and through the resistor. And then I just connect the power supply for the Arduino. So you can see that the light is on. This was moving, and we have some information on the screen. So first, let's start with that information. So the value here is the number of clicks done with the rotary encoder. I just do one click, and you can see that now it's one click. And this 0.0012 is the step size that I was talking about. So if the value is 1, that means that we have 1 LSB equivalent of voltage on the output of the DAC, and that is 1.22 millivolts or 0.0012 volts. And then here the ADC is the reading of the ADC here. It's the A0 pin, and that should be somewhat close to this result. What I'm trying to do here is I'm averaging 20 readings at a time. And now this is reading 0.09 and this is 0.072. So I would say it's close enough. So obviously I have done this before, because otherwise I would not be so confident to show this to you. So I have to increase the current quite some amount, because now we are running 0.045 milliamps or 45 microamps through the coil. And you can see that it is still stuck on the left side, and this should move towards the center because the photodiodes are not equally exposed to the light. I can demonstrate that to you by moving this thing. And if I move this thing, you should see a significant change in the voltage here. So just try to be careful. So you can see how sensitive it is. I just try to not destroy that plate here. Now the light is shining basically on the first photodiode, where the basically current enters the circuit. And now I move towards the center, and you can see how the voltage drops. And it's getting smaller and smaller. And it's nearly zero when it is centered. And then I release this, then it falls back to the other side, to the left side. So then it's a non-zero voltage again, or further from zero than it was when I was in the center. So now I try to increase this, and this will take some time. But in the meantime, you can see the values here as well at the bottom of the screen. But if I remember correctly, I have to reach something 600-ish. And you can see that this moves a bit because the current is increasing, and sometimes there's a peak or jump. Then the plate moves. And we are at like 6 milliamps. So we can still go up, because this will do something around 10, 11. But you can see that the arm wiggles more and more as we reach 10. Now I'm at 10.9. And you can see that the arm is moving. And now it's reaching the other side. And then it falls back. And you can see how significantly the voltage changes as the slit moves around, because then it provides different proportions of light to the two photodiodes here, and then the output voltage also changes, or output current, which then I convert to voltage through this resistor here. So what we can see here is that now the slit stuck on the right side, which means that we have too much current, which compensates for the weight there, because the torque is twisting the torsion line this direction, so towards the right side. So we have to decrease the current, so then the magnetic field will allow the weight to twist the tension line and then move the slit towards the left a little bit. And now actually that slit is not touching the wall here, so we are getting there. But as I told you a few minutes ago, the circumstances are not perfect. I'm talking, so I'm constantly generating a wind here, which moves the things. And I'm also touching the table and stuff, so yeah. But now you can see that it's getting more and more centered. And of course in the lab, you let this balance for like half an hour, and then you start the measurement. Here we don't want to wait, because people don't like my longer videos. So I will try to be more drastical here. But you can see that the voltage is still 1 point something, which implies that we are still heavily shining light on the right photodiode instead of the two photodiodes equally. So I move back a bit more. So we are now 764 value, or 0.9082 volts through the coil. And yeah, that translates to 10.9 milliamps in this case. And again, you can see now it drops so much down because it moves to the left side, so we are getting there. And this was too much. And maybe we can do one more thing. So hopefully the video is not super dark, but what I'm trying to do here is that exclude the light of my lamp, which is above our head. And then you can see that sometimes the voltage drops almost to zero. So maybe just one more click. So now this was 30 millivolts. So now this is again right, and now it's going towards the left. Yeah, that was 3 millivolts. If it could stop here, then that would be like basically balanced. As you can see now, that's 3 millivolts. A very, very small amount of voltage. So I try to play around with the lights. And now you can see that the voltage, or the current, because actually the current is translated into voltage, now it's getting closer and closer to zero, but also when it fluctuates towards the positive values, like it is doing it right now, it's not even leaving 100 millivolts. and this is now 60 millivolts. So now we are on the bit left side, and as soon as we move to the right side, then this voltage will decrease, and then that will mean that we are in balance. But it seems like that we moved a bit towards the left too much. So now I'm moving it to the right. Now this is too much. But the important thing is that somewhere at this current, the system is almost balanced. So then we could note down this current or the equivalent voltage, and I use that as one of our calibration points. And then we could just simply add more weight to this side of the balance arm, and then wait for the system to balance again. Then there will be a different current needed to run the coils to balance that extra weight, and then we note it down. And then we do this through, like, I don't know, 5, 10, 20 points, and then have the calibration curve. And then from that point, we can just simply read the current which is needed to balance out the arm, and then translate that current to the corresponding weight, which is hanging on this side of the arm. So once again, if you have calibrated weights in the order of magnitude of micrograms and a few milligrams, please contact me, and then I can help you get rid of those weights, and then I can calibrate my scale, and that would be exciting because then I could do some cool experiments. I'm planning to build a chamber under this wall dome, so I can use it as an analytical scale or balance, and I could measure like very tiny weights just for fun. Why not? And if you like this kind of videos about these instruments and electronics and stuff like that, please consider supporting me on Patreon, because that could allow me to buy more stuff and demonstrate them. And please don't forget to visit my website as well, because I wrote an article, link is in the description, where I took some nice pictures of this wall setup, and I explain more stuff about this instrument. So check out my website. And I think I conclude the video here. I just wanted to show you this very cool instrument and mechanism, because I think it's a very smart little device. So I hope you like this video, I hope you learned something, and see you in the next video.